Hello YouTube viewers, welcome to this video. I'm Venkat and this is Just Me an Open Source channel. Right, this video is going to be a follow-up video to the Kubernetes The Hard Way. So I did part one where I explained the theory, and then part two, complete hands-on, which took about an hour, a little over an hour. And one of the viewer commented that I forgot to do the HA testing. So basically, when you set up Kubernetes the hard way, we set it up with a multi-master with 3 controller nodes. And I did various testing at the end of the video, but the main testing, the high availability, which I forgot to do. So I thought I should do that for completeness sake. So this video, which I didn't actually plan, excuse me. So it's going to be a very quick one, just do that testing. So I've still got the environment from the previous video. So if you remember, so this is the nodes that I've shown you in my previous videos. So the host machine is still the same. It's a Dell laptop, 8 CPU, 16 gig RAM. And the setup is very similar. I just recreated the setup which I did for those 2 videos. So we have a HA proxy. We have 3 controller nodes. Each of them are running their own HCD containers. And we had 3 worker nodes, and all the interactions were going via the HA proxy, the load balancer, into the API. So for this video, I'm going to test the high availability. So we have 3 masters, controller 0 through to controller 2. So what happens if you take one controller down, and what happens if you take more than one down? So that kind of testing we'll be doing. So infrastructure-wise, setup-wise, there's no change. It's exactly the same what I shown in the previous 2 videos. Okay, so let's dive into the testing. Okay, if I show you my setup, LXC list, it should be very familiar to you if you have followed my last 2 videos about the Kubernetes the hard way. So we have 3 controller nodes, 1 HA proxy node, and 3 worker nodes. The IP addresses might have changed since the last video because I destroyed the environment and then I recreated it very similar. So I spent about 30 minutes in recreating this, the same setup. So, okay, so at the moment, all the 3 controller nodes are running, and all the worker nodes are also running. kubectl version --shot 1.12. Basically, when we followed the hard way from the GitHub official documentation, the recommended version to try was 1.12. So we went with 1.12, although the current version is 1.14.2, I think. Okay, so let's try and deploy an Nginx app. But before that, let's do kubectl get nodes. So we have 3 worker nodes. kubectl get component status. It's all working fine. We have 3 etcd nodes in a cluster. kubectl get all. We haven't got any resources deployed in our cluster. Let's deploy one. kubectl run nginx --image nginx --replicas 3. Okay, so that's created. If I do kubectl get all. Okay, so 3 nginx pod, all of them are running. If I do -o wide, and you can see the scheduler has scheduled each of these pods in a separate worker nodes just to share the load. Worker 0, 1, and 2, the pod CIDR network, everything is looking fine. So now we're going to take one master node down and see if we are still able to access the cluster. Okay, so LXC list. Let's take the controller 2 down now. LXC stop controller 2. Okay, so LXC controller 2 should be down now. LXC list. And you can see here controller 2 is stopped. Basically, the machine is shut down. Let's see if we can access the cluster. kubectl get all. Right, still we can access the cluster with 2 master nodes running. That's great. Let's deploy, excuse me, another deployment. kubectl run nginx2 minus minus image nginx. This time replicas count to 2. That's done. kubectl get all. Containers getting created. Okay, so they're all running now. kubectl get all. Okay, we have 2 deployments and 5 Nginx pods running with 1 master node down, and the cluster is still functional. So this is how you take a machine down. If you want to do some maintenance, if you want to do an OS upgrade, or if you want to replace any faulty hardware for maintenance, you don't have to do anything. Just go log into the master node and then shut it down. That's it. It will take care of all the interactions from worker nodes and the individual components, the proxy, kubelet, and the users connecting to your cluster. Everything will be going via the load balancer. So the HA proxy configuration we did in the part 2 video will send the traffic in round robin fashion to these controller nodes. So since controller 2 is out of service, it will load balance between controller 0 and controller 1. So we should all be good. So don't worry about anything. Um, okay, so we have this one now. And let's try and bring the controller 2 up again. Just imagine that we have done some maintenance work and we want to bring that machine up. LXC start controller 2. Okay, so controller 2 should be coming up in a minute. LXC list. Okay, controller 2 is back online. And if you want, you can go into the controller node, controller 2 dash. I'm inside the controller 2 master node. And you can check systemctl status kube API server. Kube API server is running. So you don't have to do anything when you bring the machine up, because everything is a systemd service. Kube API server, scheduler, controller manager, everything is a systemd service that's set to start automatically. You can see here the service is enabled. Systemctl is enabled. Kube API server. So on all our controller nodes, the services are enabled to start automatically on system startup. So there is also Kube scheduler that's also enabled, and then I think it's Kube controller manager. Yeah, that's enabled as well. Okay, so now if I do LXC list, all the master nodes are back up, and kubectl gets all. Everything is working fine. Now let's take the controller 1 down. LXC stop controller 1. Okay, so controller 1 is down. LXC list, and you can see controller 1 is down. kubectl get all, and we can still access the cluster, and we can see the 2 deployments. So what I'm trying to show here is, so now controller 2 has come up. And then we created the second deployment when the controller 2 was down, right? So controller 2 doesn't know about this deployment. So when we shut the controller 2 down, it doesn't know about this deployment, the nginx2 deployment. So we deployed that deployment resource while the master node was down. So as it is a round robin fashion and controller 1 is down, whenever we do kubectl get all, the load balancer load balances the request between controller 0 and controller 2. So if I do it for the second time, it should go to the second server, controller 2, and then third time goes to the controller 0. So in both the cases, you see the same set of deployments replica sets. So which means when the controller 2 came up, it synced its state from the other masters. When I say controller 2, it's actually the data store etcd running on. So the etcd data store running on controller 2 doesn't know about the second deployment that we deployed. And when it came up, the etcd cluster synced again. So it knows, this etcd node knows who is the current leader, and it has got an internal mechanism to check whether its data store is in sync with the other nodes, other HCD nodes in the cluster. So if it's not, it's dynamic, it's real time. So whenever it sees there is a discrepancy or it's out of sync, it syncs immediately. So that's how you see the second deployment here in controller 2 as well. Okay, so let's bring controller 1 back. LXC start controller 1. Okay, controller 1 is up. Okay, so whenever you do LXC start, it uses some system resources. That's why you see my video going stuck frozen for a second there. Okay, clear LXC list, and controller 1 is up back. kubectl get all. Okay, so still we are connected to the cluster. And if I do LXC stop controller 0, let's take controller 0 down this time. Okay, controller 0 has gone down. LXC list, controller 0 is stopped. kubectl get all, and you can see the pod's running. Okay, so controller 0 is down. So now let's try and do something else. kubectl create kubectl run nginx 3 with 3 replicas. That's created. kubectl get all. kubectl get all. Okay, they're all running. So that's the third deployment that we deployed, and these are the pods created 9 seconds ago. So the moment controller 0 is stopped and the HCD data store doesn't know about this deployment, so when it comes up, it should pick up this new deployment from the other HCD nodes. Let's see if that happens. LXC start controller 0. Okay, so controller 0 should be up. LXC list. Alright, controller 0 is back online. And let's do kubectl a couple of times so that we check whether we are getting the same output whenever we try to connect to the different masters through the load balancer. kubectl get all. Maybe if I use the watch command, kubectl get all, you can see all the pods and all the deployments. So every 2 seconds it contacts the Kube API server through the load balancer. So each time it contacts a different different master node. So as you can see, we have gone through 4 cycles, and each time we see the same thing. So which means the HCD nodes are in sync with each other. Okay, cool. So far, so good. So when what I thought was, okay, so we've got 3 masters. We took 1 master down. And the cluster was still functional. You can access the cluster. What if you take 2 master nodes down at the time? So still you have got 1 master node left. And we should be able to communicate with the cluster through that master node, but that wasn't the case. It wasn't working when I tested. Later I found from the official documentation that it's not a good practice to have a cluster with 2 master nodes. I'll show you where I found the documentation, but before that, let me show you what happens. LXC list, we've got all the master nodes running. Let's stop controller 2 and controller 1. Okay, LXC list. Okay, controller 1 and controller 2 are stopped. We are now down to 1 master. Now if I do kubectl get all, and you can see it hangs there forever. It won't give you any output. Basically, you can't access the cluster. The cluster might be still functional, or it might not be. The Nginx pods will be still running on the individual worker nodes, but as you can't contact the API server, and as you know, all the interactions between the components in the Kubernetes cluster are through the API server, and you can't reach the API server at the moment. Although the Nginx pods are running individually, If you expose that as a service, you will still be able to access the service from outside the cluster. Your application will be running, but if a node crashes, it won't be able to reschedule the pod onto a different node, or it can't do any cluster work at the moment. Okay, let's try one more time. kubectl get all. Nope, you don't get any results back. Okay, so let's try and bring one of the master node. lxc start controller 1. Okay, lxc lists. So we have controller 0 and controller 1. Okay, let's now check if we can access the cluster. kubectl get all. There you go, you can access the cluster now. So basically, if you've got 3 master nodes in high availability mode, don't take more than 1 master down at a time. So if you want to do some maintenance work, um, take a master node down, do the maintenance work, bring it back online, and make sure the cluster is accessible before taking another node down. So if I go to a web browser, I'll show you where I found the documentation. Kubernetes high availability. Set up high availability Kubernetes masters from kubernetes.io. I think it's in this link. So best practices for replicating masters for Hache clusters. Yep, it's this one here. Under best practices, you can see here, do not use a cluster with 2 master replicas, right? Consensus on a 2 replica cluster requires both replicas running when changing persistent state. As a result, both replicas are needed, and when you're having a 2 master node, a failure of any replica turns cluster into majority failure state. A 2 replica cluster is thus inferior. So bear that in mind. So when you're having a 3 node cluster and you have taken a node down for maintenance, don't take any more nodes until you fix that node and bring it back online. If you want to take more than 1 node, go with 5 node multi-master cluster. So you can still follow this Kubernetes the hard way video. It's going to be the same thing. We ended up creating a 3 node multi-master cluster. It's going to be the very same set of steps if you want to create additional master nodes and join it to the cluster. Yep, so go for 3, or if you want to take more than 2 nodes down, go for 5 node master, 5 master node high availability cluster. Okay, cool. I think that's all I wanted to show you in this video. And there's one more thing I wanted to show. This is not a truly highly available environment. Maybe in the future I will do another follow-up video on this series, because we've got the master nodes in a high available environment, HCD nodes in a high available environment, so we don't have to worry about. And we're not bothered about the worker nodes. If they go, we can add them back. They're not single point of failure. But what about the Hache proxy load balancer? So we have configured one load balancer that sends the traffic to the underlying master nodes. And what if that load balancer goes down? So that's a single point of failure. You won't be able to access your cluster. Imagine that you're in a corporate environment and there are lots of teams using the cluster, and everybody is using the cluster, and the single point of entry is this load balancer. And if that node goes down, that's it. Your cluster is not operational. So for that, what we can do is we can have multiple Hache proxy, multiple load balancers on top of the master nodes. Say, for example, I've got one Hache proxy. I could have set up another Hache proxy here. And how would you load balance between those 2 Hache proxies, and what's the IP address you will give to the end user to connect to the cluster? So that's where keep alive D comes into picture. So you have 2 Hache proxies set up in a very similar way. And then you've got the keep alive D software, a daemon running, and you attach a floating IP, a virtual IP. So this load balancer will have its own IP address, and the other load balancer will have its own IP address, and you will be creating a second virtual IP. So there is an IP command or ifconfig command where you can add a secondary IP address to the existing interface. If you have a physical machine, you can have multiple network interfaces, or you can use an existing interface, just one interface is enough. The interface where it has the current IP address, and you can create an alias to that IP to that interface and create another IP address. So we will have a common IP address, which is a floating IP address, which means the floating IP address can be assigned either to this load balancer here or to this load balancer, depending on whichever is online. So the way it works is there's a keep alive D daemon that's installed on these two load balancers. So the keep alive D daemon talk to each other on these two load balancers. So they've got, I think, I haven't experimented with that, but basically the concept should be something like this. So there's a heartbeat file. If you say currently this load balancer is active, and there will be a heartbeat file in this load balancer, and the keep alive D process running on this load balancer will constantly update the timestamp on the heartbeat file on this node. And there is this load balancer where is another keep alive D process running, and then it will constantly check. I think it should be configurable every 10 seconds or every 5 seconds, or in a very busy environment every couple of seconds. It checks the heartbeat file on this HA proxy node, and if it can't reach the heartbeat file, or if it can't talk to the other keep alive D daemon, this one assumes that the other server is down. So this one takes up the primary role, which means this will be the master, and the floating IP address will be assigned to this load balancer. So on your DNS server, you will have the DNS name pointing to that floating IP. So you don't have to change anything. You still point to the same DNS name. You're still coming to the same IP. But depending on which load balancer is active, the IP address will be assigned to that load balancer. So basically, you will have a interface. You will add an alias with a secondary IP address, which is the floating IP address, but that won't be available. That interface will be down on the backup load balancer. So the interface, the secondary interface that you have added, will only be active on the node where keep alive D is running, and then it thinks that the machine is alive. So if the load balancer goes down, the other load balancer kicks in. I mean, the keep alive D activates a secondary IP address, the floating address on this load balancer. So that's how the keep alive D works, but that's not for this video. I'll be doing that on a later video. Right. Okay. So cool. Thank you so much for your time watching, and thank you for the viewer who mentioned about this testing, which I forgot to do. So if you find anything interesting, or if you find something that's not working, just leave me a comment, and I'll try and explain that in comments. But if it's become if it's more complex, then I'll try and do a video of it so that it'll be useful for the for other viewers as well. Okay, thank you so much for your time watching this video today, and I'll be seeing you on my next video. Bye bye.